we should start. Okay, good morning. So today we are first going to talk about quasi-convex and quasi-concave functions. Actually, I'm going to talk only about quasi-convex functions because quasi-concave functions are just the negative of quasi-convex functions. So in everything I'm going to explain, you simply change the signs and you get the corresponding results for quasi-concave functions. Quasi-convexity is one of the many generalizations existing of convexity, but in my opinion, by far is the most important. There are many useless generalizations, others that are useful, but quasi-convexity is the main, in particular in view of its applications to economic theory. I mean, every economist, every student of economics knows the notion of quasi-convex function because they are essential in production theory because, as we are going to see, a regular production function should be quasi-concave. Also, in consumer theory, we will see that the so-called indirect utility functions, which are the functions that express the consumer preferences regarding prices, they are always automatically quasi-convex. And only exceptionally they are convex. And in fact, convexity of an indirect utility function is meaningless because if you change the utility representation of the preferences, then even if your initial utility function was convex, then another utility function would not be convex. Then convexity has no economic meaning in this particular case, and quasi-convexity has. So it's really a very important class, the class of quasi-convex functions in optimization and economics. As we are going to see soon, in optimization they appear, for instance, when we are solving fractional programming problems. Okay, so let us start with the definition of a quasi-convex function, comparing it with the classical definition of convexity. So as you know, a function is convex defined on a convex subset of Rn when this inequality holds. For every xy in the domain of the function and for every lambda between 0 and 1, which the reason for this definition is that it is equivalent to the convexity of the epigraph. Okay? A function is convex when its epigraph, everything which is above the graph of the function is a convex set. If you express convexity of this set, you will easily obtain that it's equivalent to this inequality. Now, we can relax this inequality by replacing in the right-hand side both f of x and f of y with the maximum of the two. Okay? So if you replace here with the maximum, you are increasing because the coefficients are non-negative. And then you get 1 minus lambda plus lambda, which is 1 times the maximum, so you get the maximum. So we are proving that every convex function satisfies this inequality. Okay? Then a function which satisfies this inequality is said to be quasi-convex. So what we are here proving is that every convex function is quasi-convex. But it is easy to see that there are quasi-convex functions, we are going to see, that are not convex. So to start the definition more formally, suppose we have a convex subset of Rn and we have a function f defined on it. I'm going to consider extended real valued functions. So these functions will take values in the extended reals which include minus infinity and plus infinity. For convex functions, you can do it too, but it wouldn't make much sense to admit the value minus infinity, because it's very easy to see that if a convex function takes the value minus infinity, it takes only finite values on the boundary of the domain. So it takes the value minus infinity on the interior of the domain, plus infinity on the exterior, and only on the boundary may take finite values. So it's not very interesting. So minus infinity is not useful for convex functions. Plus infinity is very useful, because rather than considering different functions each own with its domain, which creates troubles when operating with the functions, you need a common domain. Then what you do is to consider that all of them are defined on the whole of Rn, and then outside of the effective domain of the function, they are considered to take the value plus infinity. And this works well. But for quasi-convexity, minus infinity makes sense. It's not the same as in the case of convexity. So for convenience, I admit that our functions take the value minus infinity. Then we say that f is quasi-convex if this inequality holds. For every xy in C and every lambda between 0 and 1. But in the same way as you have a question? No.
Why in convex set you said it is good to take infinity, not minus infinity, but for quasi-convex? Because when we give definitions, some authors define it for convexity also for just two reasons.
You can. Certainly you can define convexity admitting the value minus infinity, no problem. But then you realize that the class of functions which are convex and take the value minus infinity is very restrictive.
Or they are very less examples.
They are useless examples, I would say. So if, as I said, if you have a convex function which takes the value, suppose a one variable function, okay? So it takes the value minus infinity at a point. It may be identically minus infinity. Why not? This is not a very useful function, okay? But then if a takes a finite value at some other point, beyond that point, it must have take the value plus infinity. Okay, so only at a point, at 2 points, let's say the endpoints of the interval where it takes the value minus infinity, only at the endpoints it can take a finite value. Outside that interval, it has the value plus infinity. And similarly for several variables. So these functions do not appear in practice. They are not interesting.
Because I'm not able to imagine how to imagine this function who is taking minus infinity at some point and then it has to take some finite value. So like how to imagine a convex function in that form?
Oh,
If minus infinity takes,
I don't know, just to give a simple example, suppose the function of one variable, which is f of x equal minus infinity if x belongs to the interval minus 1, 1, 0 if x is minus 1 or 1, and plus infinity in every other case. So a function with this graph, I mean, this is minus 1, this is 1. So here is minus infinity, here is plus infinity, here is 0, and here is 0. Look at the epigraph of this function. The epigraph of this function is, well, in fact, not. This should not be convex. So I should take plus infinity. Okay? Okay, so outside this point, it should be plus infinity. So the epigraph is this set, the union of this half plane with this half line, which is a convex set. So only at one point, even I was wrong when I said that 2 points. No, only at one point it can be finite. This is an example. You can build examples in more variables using the same idea, but that's the only case, the only possible case. Because, so assume you have this situation. I don't define this function beyond minus 1. I define it here. So which values can I take here? If I consider a point on this side where it takes a finite value, then I am adding this set to the epigraph. But the union of this with that cannot be convex, so the function cannot be convex. So it's very exceptional. So formally you can admit the value minus infinity for a convex function,
it's not a useful one.
but it's not useful. Okay, so in fact, in my opinion, it is useful, but only when the function takes the value minus infinity identically. So people, maybe in Rockefeller's book, they define convexity, proper convex function when it doesn't take the value minus infinity and it doesn't take the value plus infinity identically. So the value plus infinity is admitted, but not everywhere. In my opinion, this is not a good definition. Because for me, the most useful definition, if you want to have short statements, is to admit as proper convex functions, on top of these ones, the constant functions minus infinity and plus infinity. For instance, with Rockefeller's definition, you say the supremum of a collection of convex functions, of proper convex functions, is either a proper convex functions or identically plus infinity. If you admit plus infinity to be a proper convex functions, then you simplify the statement. The supremum of a collection of proper convex function is a proper convex function. Even the supremum over the empty collection, which should be identically minus infinity. Okay, so I prefer, when I define proper, I said, okay, here I depart from the classical notion simply by admitting that the constant functions minus infinity and plus infinity are proper. But with quasi-convexity, things are very different. So it's not artificial to admit that a quasi-convex function takes the value minus infinity. And in fact, for one of the results I will prove today, I will need the value minus infinity. Okay? Then, in the same way as convex functions are characterized by convexity of their epigraphs, it's very easy to prove, and I'm going to do the simple proof, that quasi-convex functions are characterized by convexity of their lower level sets. Well, I said I'm not going to insist all the time between quasi-concavity, but at least from time to time I'll do it. If you change the sign here, then you get the notion of quasi-convexity, but changing the sign of this expression means that quasi-convexity means that this image of a convex combination is greater than or equal to, we have changed the signs, the minimum of f of x and f of y. That's the definition of quasi-concavity. Okay? Then, so the first very simple result is that a function f is quasi-convex if and only if the lower level sets are convex. For every level alpha, the corresponding lower level set is convex. This obviously happens for convex functions. If you fix a level, then the corresponding sublevel set or lower level set is convex. But for this convexity, you don't need convexity of the function. For this function, well, which is, it's not correct. Now it is. Which is first decreasing and then increasing if you fix a level. Then you find that the corresponding lower level set is convex, even and the same with every level, even though the function is far from being convex. Okay? So let us see this property, which is very easy to prove. Yeah. So assume first that the function is quasi-convex, and let us prove that the lower level sets are convex. Let's fix a level alpha and take 2 points in the corresponding lower level set and a coefficient in the 0-1 interval. Then if you take the image of the corresponding convex combination, because you are assuming quasi-convexity, you have this inequality, but both f of x and f of y are less than or equal to alpha because both x and y are in that lower level set. So this is less than or equal to alpha, which is telling us that 1 minus lambda x plus lambda y belongs to the lower level set. Trivial. The converse is also very simple, but I mean, I have to use a very little technicality for the fact that the levels are real. And we are admitting minus infinity and plus infinity as possible values, okay? So, but anyway, so let's assume that all sublevel sets are convex, and let us prove that f is quasi-convex. So take 2 points in the domain, lambda between 0 and 1, and we have to prove that this inequality holds. There are 2 cases. If the maximum between f of x and f of y is plus infinity, there is nothing to prove because everything is less than or equal to plus infinity. So assume that this max is less than plus infinity, but it could be minus infinity. So I cannot take it as a level. But then I consider any real number, alpha, greater than this maximum. It exists because this maximum is not plus infinity. Then we have that both f of x and f of y are less than alpha. The maximum is less than alpha, which means that both x and y belong to the lower level set corresponding to alpha, and then since this level set is assumed to be convex, then the convex combination belongs to the set, which says that f of 1 minus lambda x plus lambda y is less than or equal to alpha. But alpha is any number greater than this maximum. So f of the convex combination must be less than or equal to this maximum, which is what we needed to prove. Okay? Again, this is a very simple argument, but if you don't see it, simply make alpha tend to this maximum, and then from here you get the desired inequality. Well, let us see examples of quasi-convex functions. Pardon?
Can you repeat that point? Max less than max?
Yeah. I mean, this is an argument I already used yesterday in another context. If you have a number let's say A, which is less than or equal to every number which is greater than another number B, okay, then it must be less than or equal to B. This is direct. I can make a direct proof. I mean, it's immediate. So I'm saying if A is less than alpha for every alpha greater than B, this is what I am saying, then A is less than or equal to B. This is immediate if you think carefully, but if you don't agree, I am going to make two proofs. First proof, by contradiction, assume is not the case. Assume A is greater than B. Then choose an alpha strictly between A and B, okay? Then, okay, then since this alpha is greater than B, by assumption, A is strictly less than alpha, but this is a contradiction, okay? So this is the formal proof. But I said, if you don't like this proof, there is a simpler proof which I don't like. Take the, because alpha is any number greater than this, or look at here. Since alpha is any number greater than B, in this expression, take the limit as alpha tends to B. And then you get A less than or equal to B. This is maybe more direct, but I don't like it because I am using the definition of limit, which is not necessary for this proof. I mean, I can use this argument in ordered sets in which there is no topology, no limit, etc. So it's a matter of ordering, not a matter of topology of limits. Okay? Do you agree or not? Okay, thank you. Then examples of quasi-convex functions in one variable. Monotonic functions, non-decreasing. Fix a level. What is the sublevel set? If this half line, which is a convex set, then the function, and this is the same for every level, so the function is quasi-convex. By the way, let me say still a few words about quasi-concave functions. Quasi-convex functions are characterized, as we just proved, by convexity of the lower level sets. Then quasi-concave functions are characterized by convexity of their upper level sets. Okay? Then this function is quasi-convex, but it's also quasi-concave, because what would be the upper level set? Would be this half line, which is also convex. So non-decreasing functions on the real line are both quasi-convex and quasi-concave. For this reason, some people called in general, in the case of several variables, functions that are both quasi-convex and quasi-concave, quasi-monotone. But I prefer to use the term quasi-affine, because functions that are both convex and concave are affine. Then I think it's natural to call functions which are both quasi-convex and quasi-concave quasi-affine. Okay? But quasi-monotone, I still can admit that terminology when the domain is not the whole space. Okay, then it's acceptable in my opinion, but not when it's the whole space, which I don't like at all. I mean, so quasi-monotone I admit, but what I don't like at all is that some people call those functions quasi-linear. I see no reason to call them quasi-linear. Okay. If you admit this terminology, an affine function would be quasi-linear. Well, I mean, you are free to use whatever term you like, but I think it's inappropriate. F non-decreasing, but also F non-increasing. Fix a level. Then the lower level set would be this half line, and the upper level set would be this half line. So non-decreasing, non-increasing functions are also quasi-affine, both quasi-convex and quasi-concave. In all my pictures, by simplicity, the functions are continuous, but they need not be. And this is an important difference between convexity and quasi-convexity. A convex function is automatically continuous on the interior of its effective domain. This is not the case of quasi-convex functions. Although they are continuous almost everywhere, they have such properties which were proved by one of the mathematicians I most admire, which is, in my opinion, by far the best in quasi-convexity, who is Jean-Pierre Crouzet from France. Have you heard his name? Well, he's not very active in the last times because he's not so young, let's say. But the deepest results on quasi-convexity are due to him, my opinion. Well, okay, but let's move to more than one variable. A simple example of a two-variable function which is quasi-convex but not convex. Okay, this function. It is not convex. You know, second order characterization of convexity, the Hessian should be positive semi-definite, and it's not. So this function is not convex, but it's quasi-convex. What are the alpha sublevel sets of this function? So xy belongs to this sublevel set means that minus xy is less than or equal to alpha. Well, we have to distinguish among several cases. So if alpha is positive, this is the whole space, because x and y are non-negative, but there is some minus sign here, so the left-hand side is always negative, or at most 0. So if alpha is non-negative, then the sublevel set is all of r plus 2, which is convex, the quadrant. Then if alpha is negative, then first of all, x cannot be 0. Then you can solve here for y, and you get this expression. So the sublevel set is characterized by this condition. The denominator is positive. Then consider the function defined by this right-hand side. It's a function of this type. Okay? The graph is the branch of a hyperbola, which is convex. And sorry, there is some mistake here. Which I don't understand. No, we divided by, yeah, because I consider the minus. Yeah, I was thinking that I divided by x, but no, I divided by minus x. Thank you. So this defines the epigraph of this function, okay, which is convex. The function is convex, its epigraph is convex. So all the lower level sets are convex, so this function is convex, is quasi-convex, although it is not convex. This is an example. Another very important example for applications: fractional functions. So you have two functions defined on a convex set. And we assume that G is convex and non-negative everywhere, and H is concave and strictly positive everywhere. And then you divide G by H. In general, this function is not quasi-convex, is not convex at all. Only exceptionally it would be convex. But it is always quasi-convex. Let as look at its lower level sets. We fix a level alpha. And what are the elements of these lower level sets? They satisfy the inequality f of x less than or equal to alpha, which is g of x over h of x less than or equal to alpha. And you can move h of x to the right hand side and then everything to the left hand side, so you get g of x minus alpha h of x less than or equal to 0. So this is the inequality characterizing the lower level sets. Now, what about alpha? Oh, sorry, belongs. I don't know why I wrote. Thank you. So remember that G and H are both positive. Okay? So if this lower level set is non-empty, then alpha must be non-negative. So for alpha negative, this is the empty set, and the empty set is convex, no problem. Now assume that alpha is non-negative. With a minus sign, it becomes negative, and it's multiplying a concave function, which makes the product convex. So we are adding convex functions. The sum is convex. So this is the 0 sublevel set of a convex function. Since convex functions are quasi-convex, this lower level set is convex, and it's the same as this lower level set of f. Okay? The same example also works if G is convex, but not necessarily non-negative. It may take negative values, and H is positive. Of course, we need strictly positive. If we are dividing by h of x, we cannot accept the value 0, and by continuity, then it must be either positive or negative everywhere. So H is positive and affine. Well, in this case, the argument I used that the lower level sets are empty for negative alpha is not true. Now alpha may be negative and the corresponding lower level set would be non-empty, but I don't care about the sign of alpha because I will be adding to G an affine function. Convex plus affine is convex plus convex, so convex. Okay, so in this case, I don't care about the sign of alpha, so G in the numerator need not be non-negative everywhere. So these examples are useful in fractional programming when you are minimizing a function of this type subject to some convex constraints or whatever. Also, in generalized fractional programming, in which the objective function is a function of the type maximum of f1 of x over g1 of x, fk of x into jk of x. So with functions having these properties, okay, then they are also quasi-convex, and they appear in practice. Jean-Pierre Crouzet, whom I mentioned, together with Siegfried Scheibel and probably Jacques Ferland, I'm not sure now, they studied the economic von Neumann economic growth model by means of generalized fractional programming. So these problems are not artificial, they appear in practical applications. Okay? So this shows the importance of quasi-convexity. Here, I am using the fact that the maximum of a collection of quasi-convex functions is quasi-convex. The same is true in a more general situation, the supremum of a collection, finite or infinite, of quasi-convex functions is quasi-convex. So if I say, if I have fi quasi-convex for every I in some index set, then the supremum, pointwise supremum of this family of functions is also quasi-convex. The proof is immediate. You can do it by using the algebraic definition of quasi-convexity, or the way I prefer is by considering the sublevel sets of the supremum. Okay, so the sublevel set of the supremum is the intersection of the sublevel sets of the members of the family. This is an immediate equality because saying that X belongs to the left-hand side means that supremum of fi of x is less than or equal to alpha, and saying that x belongs to the right-hand side means that f of I of x is less than or equal to alpha, because x is in this sublevel set for every I, because it's in the intersection. And of course, these two conditions are equivalent. Then, since the sublevel set of the supremum is the intersection of the sublevel sets, if the functions are quasi-convex, then all these sublevel sets are convex, and the intersection of convex sets is convex. So the level set of the supremum would be a convex set, so the supremum is a quasi-convex function. So easy. So this justifies what I said here, that in generalized fractional programming problems, the objective function is quasi-convex. Or even the empty set. Well, if it is the empty set, the supremum is identically minus infinity, which is clearly a quasi-convex function. But yes, I made no assumption about finiteness or of I. I is an arbitrary index set. Yes, 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 of course. Then, when I gave you examples of one variable quasi-convex functions. I told you increasing functions, decreasing functions, but what's the general form of a quasi-convex function of one real variable? Okay, let us see it. So I'm going to prove that on the real line, C convex, of course, F is quasi-convex if and only if there exist two functions, F1 and F2. F1 is non-decreasing, and F2 is non-increasing. I use non-decreasing to mean increasing, but not necessarily strictly. Okay, the same with non-increasing. Such that F is the maximum between F1 and F2. So what's the meaning? Graphically, geometrically, you have a non-decreasing function, you have a non-increasing function, and you take the maximum of the two. Okay? So in practice, this means it's a function which is first decreasing, and then increasing. It's equivalent. It's very easy to see this equivalence. And this proof is not difficult. From right to left, there is nothing to prove, because both F1 and F2 are quasi-convex, because we saw that monotonic functions are quasi-convex, and we are taking the maximum. We just saw that the supremum preserves quasi-convexity. So from right to left, there is nothing to prove. From left to right, it's not. It's very simple, but not extremely simple, because we have to construct F1 and F2. Then I consider F1 of X equals to the infimum of F of T for T greater than or equal to X, and F of 2, F sub 2, this is a definition, is the same but with T less than or equal to X. Let us see that these two functions do the job. So first, F of 1 is non-decreasing, because if you increase the variable, if you increase X, then you are reducing the feasible set in this minimization problem, so the infimum increases or remains the same. Similarly here, if you increase x, then the feasible set in this minimization problem becomes larger, and so the infimum becomes smaller or at most the same. So these two functions are monotonic, and then take the maximum of the two in fact, both functions are minorands of f because among those t that are larger than or equal to x, there is x itself. So f of x is one of these, of the possible values here. So f of x is larger than the infimum, which is f1 of x. Okay? Similarly here, f2 of x is less than or equal to f of x because among those t, there is x itself. So f of x is one of the possible values in this set. So it's larger than the infimum, which is f2. So we have that the maximum is less than or equal to f, but I am going to prove that it coincides with f at every x. So let's fix x, and consider any alpha greater than this maximum. Okay? This means both f1 of x and f2 of x are strictly smaller than this alpha. But f1 of x is defined as an infimum. Infimum smaller than alpha means that some element in this set is smaller than alpha. So there is some t, let's call it t1, greater than or equal to x, such that f of t1 is smaller than alpha. Okay? Similarly here, this less than alpha, this infimum less than alpha means that for some feasible t, which I call t2, the corresponding value is strictly less. Sorry? Thank you. The t2 less than or equal to x. Thank you. And so, but look at this situation. X is between t1 and t2. Thanks to your correction. And so x can be expressed as a convex combination of t1 and t2. Then by quasi-convexity of f of x should be less than or equal to alpha. Okay? Then, now I'm using again that argument that I have already used several times that we discussed. F of x is less than or equal to any number which is greater than this maximum. Then f of x should be less than or equal to this maximum. Okay? Again, if you disliked my order theoretic argument, set alpha tend to this maximum, and then you get what I told you. And this is the opposite inequality to the one we already had. So we have the equality. So now you know the structure of quasi-convex functions of one real variable. By the way, there is a generalization of this result to several dimensions, but it's not so easy to state. It's a result I published when most of you were not born. I think I published it in 1988 or so, which says a function of several variables is quasi-convex if and only if it is the pointwise maximum of a collection of functions, each of which is monotonic with respect to a total ordering compatible with the linear space structure of Rn. This is a particular case of that because in the real line there are only two orderings compatible with the linear space structure, less than or equal to and greater than or equal to. So here we are considering non-decreasing with respect to less than or equal to and non-decreasing with respect to greater than or equal to, which means non-increasing. So this is a particular case of the result I got so long ago. Okay. Okay, we can stop now and we'll continue this afternoon.
So we have a break for 10 minutes, and then from the next class will be from 11:30.